Today I'm going to talk about tangent decoupling, which I also call it conditionally independent decoupling. And the reason why this is helpful is because by using some inequalities that I will show, you can treat dependent variables as if they were independent. So you can treat dependent variables as if they were independent. And that is important, for example, in developing concentration of measure inequalities for dependent variables into inequalities for martingales. So you can extend most of the exponential inequalities for independent variables to the case of self-normalized martingales, for example. And the way the proof goes, maybe I will talk about that in more detail, but is by using a decoupling inequality, you can replace the dependent variables by independent and then work conditionally and obtain your result for dependent. So it's a handy tool to have. Okay. So I already gave some introduction to tangent decoupling, but I'm going to review things because some people thought I was going too fast. So this will help as a refresher. So, okay, so I will review how you decouple sequences, how you can decouple sequences, and I will give a couple of examples, and then afterwards I will give an inequality for the moment generating function. I will actually give you the proof of the inequality. It's a simple proof, but it gives you an idea as to how decoupling works or how you attain decoupling. Okay, so now some background and definitions. Okay, so for tangent decoupling, so we have d sub I and y sub I be two sequences of random variables adapted to an increasing sequence of sigma fields f sub I. Then d sub I is said to be tangent to y sub I with respect to f sub I if for all I the conditional distribution of di given fi minus 1 is equal to the conditional distribution of yi given fi minus 1. Okay, so the conditional distributions are the same for all I. Okay, and if the variables are conditionally symmetric, that means that the law of d sub I given fi minus 1 is equal to the law of minus di given fi minus 1. And okay, is there any question about that? Okay, so now the sequence y sub I, the one that is companion to your arbitrary sequence, is called okay, so adapted to an increasing sequence of sigma fields f sub I contained in, the largest sigma field f, script f, is said to be conditional independent, more succinctly said CI, if there exists a sigma algebra G. I will give you an example of such a sigma algebra, such that contained in F, such that y sub I is conditional independent given G. And the conditional distribution of yi given fi minus 1 is equal to the conditional distribution of yi given G. Now, so in order to work with the variables, it's important to have this equality because as you will see in the proof of the inequality, it allows you to treat, the y-i's can be treated as independent. So I will show you, I will tell you where this condition is used and what G I used to do it.
So can we just think about G as the union of all sigma algebra FI?
No,
No?
it's not the union. It's, you see, let me see if I have the, yeah, this is something, oh, okay, good. So I showed you this picture before.
Right.
And you see, this is a sequence of arbitrarily dependent variables. And then you, from this, you construct the yi's with the property that the yi's are conditional independent given the d's. So that the G is the sigma field generated by the d's. Okay? So if you know the d's, then these variables are independent by construction. Is that clear?
But F is the sigma field generated by all the D's and all the Y's also?
Yes.
I see. Okay.
So you have to enlarge the sigma field of the d's to include the y's as well. Okay, so now so if we have d sub I to be an arbitrary sequence of random variables, then a conditionally independent sequence yi, which is tangent to di, have the same conditional distribution, is called to be decoupled. A decoupled version of di's. So these are decoupled because when you condition on G, they are independent. So that's what we call decoupling. You are using an analogous sequence which is conditionally independent. Now, a very important result in this theory is that for any sequence of variables, one can find a decoupled sequence on possibly a large probability space, which is what we spoke about, just your question, which is tangent to the original sequence and is in addition conditionally independent with respect to a master sigma field. Frequently G is that. Now before I created this diagram, it was not clear how to come up with the y's. I mean, it would be, so basically the y's, there could be other tangent sequences and another sigma algebra for which these ones are conditionally independent. But this graph helped me make clear how one can construct a sequence. The other one was just, so the result by Kwapin and Rysinski says there is always a tangent sequence, a decoupled sequence. But when I saw that problem, I wasn't really clear as to how to do it. And finally, I came up with this. And this, I spoke to someone who was an expert in sampling. And this is considered a new sampling scheme. I would show you what that means. So in sampling, you have sampling without replacement, sampling with replacement, and conditional independent sampling lives somewhere in between.
So from D1 you generate Y2 and D2. So you generate two independent ones using the same mechanism, right?
Yeah, you generate two copies of D2 given D1, independent.
Does it matter which one you call D2? V2 and which one you call?
Oh, okay, yeah. That will be clear when I showed you how to do it for drawing balls from a box.
Okay.
So what you do is you do things. So suppose you have a box. What you do is you first draw y1, okay? And then you put it back, and then you draw d1. So they have the same distribution. Next stage is to take y2. Then you put it back. And then you take d2, and you put it away. You don't put it back.
Okay.
Then when you do this, the variables have the same conditional distributions given the past, but the yi's are independent. Because so even though the box is getting empty at every stage, but it's only getting empty when we take the d sub i's outside.
Thank you.
Okay?
Thank you.
So you see, I should have waited for a little bit, because I have that here. This is the way you put it. So this is more graphic. So let me just, show the diagram, because maybe this will become more clear, better than my explanation. So what you do is, suppose you have a box with balls, and then, so we have capital N balls. The sequence d sub I will represent a sample without replacement, okay? When you don't replace things, the box is changing, so the variables are dependent. In obtaining a conditional independent sequence, we proceed as follows. At the I stage of the simple random sample without replacement, okay? Both d sub I and y sub I are obtained by sampling uniformly from the box that doesn't include the first di minus ones. Okay, so it is easy to see the above procedure will make y sub I tangent to d sub I. They have the same distribution. With the sigma field Fn is the sigma field of okay. Actually, Siva made a very interesting observation, which wasn't in this slide. It will be in the next version. The sigma field, they will be tangent given the sigma field of d1 up to dn and y1 up to yn. So that's an enlarged sigma field. And the sequence of yi's is conditionally independent given the sigma field of the d's. So here is an illustrative thing. So first you take y sub I, put the ball back, and then you take d sub I and take it away. So if you do this repeatedly, you get a decoupled sequence. So here is an example of how you do this with autoregressive model. So this applies to time series in particular. So if you're interested in decoupling time series, this is one way of doing it. So what you do is, suppose that you have a sequence d sub I, you have a time series, which is defined by d sub I is equal to theta d sub I minus 1 plus epsilon sub I. With the absolute value of theta less than 1. Let's suppose that the sequence E sub I is IID0 mean zero random variable, okay? These are IID mean zero. Then a conditional independent tangent sequence to D sub I is Y sub I, where Y sub I is equal to theta di minus 1 plus epsilon I tilde, where epsilon I tilde is an independent copy of epsilon I. So what's happening here is you see the yi's use the previous information plus an independent copy that will not be included in the next d sub I. And so that's how you create the independence. So, you can do this also if you're looking at randomly stopped sums. You can decouple randomly stopped sums with a similar procedure. So you can treat the stopping time. So if you have a sum of independent variables, then decoupling gives you a sum of conditional independent variables when you condition on the sigma field of, so you have a sum of x sub I independent variables up to a stopping time. The decoupled sum is going to be so you have x sub I and you have an independent copy of the x sub i's. That's the x sub I tildes. Then the let me think how to explain this. Okay, so the second sum, so you have sum of x sub I to x sub I xt.
You can write if you want.
Oh, I can write. I didn't realize that. Okay, thank you.
You can even write on the slides if you want.
Excuse me?
You can even write on the slides if you want. You can
Oh.
write on the whiteboard, you can write on the
That's handy. Okay. Well, so let me show you how things work in randomly stopped sums, which is one of the big successes of decoupling, is treating sums of independent variables up to a stopping time where the variables are in a Banach space. So this is fairly general. So what we have is, so suppose that you have x1 up to xn, okay? These are independent. And x1 tilde up to xn tilde is an independent copy of the x sub i's. Now, these ones don't have to have the same distribution as I changes, but x sub I tilde has the same distribution as x sub I. Okay? So this is not necessarily for IID. So you can, okay. So the way, suppose you have the sum, you want to decouple the sum of x sub I going from 1 up to t. So the way you do it, so let's rewrite this as the sum I going from 1 up to infinity of x sub I indicator that t is bigger than or equal than I. That's the same. Then you can decouple this sum and to see how the decoupling works. So the decoupled sequence is going to be the sum I going from 1 up to t of x sub I tilde, and which is equal to the sum. So I'm going to show you that indeed this one is decoupled and how you go from here to here. So the sum I going from 1 up to t up to infinity of x sub I tilde indicator that t is bigger than or equal than a. Okay, now, so which ones are the tangent variables? You see the conditional distribution of x sub I indicator that t is bigger than or equal than I given the sigma field generated by the x sub j's and the x sub j tildes for j going from 1 up to I minus 1. So if I condition in the past Okay? Using Siva's suggestion, we include the tildes also in the sigma field. Then the conditional distribution of this is the same as the conditional distribution of xi tilde indicator that t is bigger than or equal than I. Okay? Given the same sigma field. So we are conditioning on the first I minus 1 pairs. And since, you know, this random variable is measurable with respect to what I would call f sub I minus 1. So if I know the x's up to x sub I minus 1, then, and the xi tildes up to I minus 1, then this is a random variable adapted to the f sub I minus 1. And so that's where, you know, it's easier to understand it. I mean, this makes it a little confusing. But if I erase what Siva's suggestion was, you know, if I just condition on the x sub i's, then it's easy to see that then these two sequences have the same conditional distribution given the x, j's, j going from 1 up to n minus 1, I minus 1, okay? Because this is adapted to the x's up to I minus 1. Okay, so this is what I call d sub I, and this is what I call e sub I.
Y sub.
Oh, y sub I, I'm sorry, I'm used to, yeah, I'm used to using d and e. Okay, thank you. I can count oranges but not apples. Okay, so let's put y sub I. So this is d sub I and this is y sub I. This is the conditional independent sequence. Okay? So that's how you decouple. Now the interesting thing here is that I'm going to talk in a subsequent lecture about extending Walt's equation to the case of variables. So you see Walt's, I don't know, how many of you are familiar with Walt's equation? So that's sort of like the foundations of sequential analysis. And there's a Walt's second equation. So Walt's second equation tells you that if you have IID means 0 variables, then and t is a stopping time. So if you have xi IID variables with expected value of x sub I equal to 0 and variance of x sub I equal to less than infinity, okay? So the variances usually they assume that they are the same, but in this case you don't need them to be the same. Then the expected value of the sum, since the mean is 0, of this square is equal to the expected value of the sum of x sub I I going for, okay. Okay, so it's equal, I will assume that they have all the same variance for a second. Okay? Is equal to sigma square times what? This is a quiz. Yes? What is it? Expected value of t. Okay. So now, a person that Govinda Rajulu, who was a professor that wrote a book on sequential analysis, he posed the question, what can you do if the variables are not mean 0? What type of Walt's equation do you get? Now, and the solution to that problem is I don't get an identity. We didn't get an identity, but we got an inequality that extends Wald's equation from mean zero to non-mean zero. And the extension works as follows. So they don't have don't have to have the same variance, but so what I have is this inequality. So here you are stopping your sequence at your stopping time. And the x by tilde is an independent copy. So it's like both you and your friend are playing the same game. So you have the x's and your friend has the x tilde. So you start sampling. So t is adapted to the x's. So t is the stopping time for the x's. And so I am using the same stopping time. So when your friend stops, he tells you stop now. Okay, so you, let me think. No, when you stop, you tell your friend stop. Okay, so that's this one. And then if your friend does that, then there will be an inequality of this type. Perhaps this is easier to understand in the case of Wald's equation, the first equation. So let me show you that. Anyway, so this is an extension of Wald's second equation, which is sharp. That is to say, there's a distribution for which this is equality. But, you know, this might not be easy to grasp, I think. I'm not saying, you know, I'm just stating a fact of my teaching ability. But with Wald's first equation, we have expected sum of x sub I, IID. Actually, let's take them independent, not identically distributed, with a finite mean. Okay, well, if they have a finite, the identically distributed, then this will be equal to what? What Wald's equation tells us what? If expected value of x less than infinity. What does this tell us? Okay, if expected value of x sub I is equal to nu, so this is another quiz. So since I was going too fast, now I'm going to make sure that you understand what I'm doing. So let's see. So this is nu. So what is Wald's first equation? What is it? Nu times the expected value of t. Now, by Fubini's theorem, so I'm going to show you how to decouple Wald's equation. How Wald's equation, what he did was he decoupled the sum. So this is the expected value of x, okay, times the expected value of t. Now, which happens to be equal to the expected value of the sum I going from 1 up to t of x sub I tilde. Let me see, times expected of t, x sub I tilde, yeah. Okay, well, so if you look at this sum, if you stop your friend's process, if you tell your friend stop now, and the person stops, then on the average, the same, they will have the same expectation. And so this is potentially useful for surgeons, brain surgeons, So suppose that you have a brain surgeon here that knows what he's doing, and then there's one in the moon, okay? And you want to have the same average result, okay? So the surgeon here, you know, your friend is doing his procedure in the moon. So they are, you know, so he's doing his own thing, independently of you. But if you want them to have the same average outcome, then the surgeon from here tells the people in the moon, the surgeon in the moon, to stop, when to stop, and then their average result will be the same. So this is a decoupling identity which extends Wald's equation to the case of non-IIT. Right? Because Wald's equation assumes that you have IIT variables. In this case, the variables can have different distributions, and you have this. Okay? So this is the Wald's equation, decoupling Wald's equation. Now, Michael Klass, I spoke to him yesterday to ask him your question. And so I was going for dinner, and you know, I had to talk to him on the phone because, you know, when he explains something, you have to pay attention. So we spoke all the way to the restaurant. Okay, I was being rude because, you know, I was paying attention to what he was saying. I almost fell, but anyways, you know, when you have your advisor, you better pay attention to what he says. So we spent about half an hour to get to the restaurant, and I asked him your question. As I said, I'll call Michael Klass, but in half an hour he wasn't able to give me a straight answer. So I'm going to spend another hour with him to try to get the answer. Okay, he was explaining to me how he did that, the K function. Anyways, he produced a Wald's equation for variables in a Banach space by doing a decoupling inequality. So you can do Wald's equation for variables in a Banach space by using so the equation that he proved is that the expected value of the sum of the norm of the sum I going from 1 up to t of x sub I tilde, x sub I, I'm sorry, is less than or equal than the expectation of the norm of the sum of x sub I tilde times a constant. So if you have IID variables, independent variables in a Banach space, and you want to study the properties of the random stop process, then you can do that by using the stopping time, by asking your friend to stop their process at t. The price is a constant, so we are talking about the price of independence. And in the case of the square, this works for all p bigger than 1, bigger than 0. For every p bigger than 0, this works. So when I spoke to my friend and he proposed the problem for Wald's second equation, we found this. So we found the price of dependence. The constant 2 is sharp for the real valued variables, but the constant for the Banach space variables is not known. And that might have some nice implications is like you are taking the sum of matrices up to a stopping time. Then you can use Michael's result to get a bound on the expected value of the sum of the Banach space variables to the second moment. That will be bounded less than a constant times the expected value of the sum of the independent copies up to the same stopping time. But the constant is not known. In this case, in the real valued case, the constant is, the sharp constant is 2, so you know what the price is. Now the challenge is to find what the price is when the variables are in a Banach space, like when you're adding matrices up to a stopping time. You know, random matrices is a fashionable topic these days. So that's an open problem in random matrices. I don't think that the people that do random matrices have worked on this. I think it's an open problem. How do you do sequential analysis in a Banach space? You know, sequential analysis with matrices. I have been to conferences in random matrices, and they show results. And I asked them, can you do that sequentially? And they said, no, that's a good problem. So there's a problem for you. That's a quiz. Okay, never mind. Okay, so I'm sorry, that was a side thing. Toward the end of the lectures, I will prove this one. Okay, I'll give you the full proof. Okay, so now let's go. Now, decoupling is inequality for products. So now we go back to arbitrary sequences, adapted sequences. So this is a special case, you know, anyways. Yeah, this is for the products, but it can also be used for sums, as I will show later. But the inequality is, so you have d sub I a sequence of positive variables. Here I assume that they are positive, okay? And I take G to be a sigma field. Then for any G conditional independent sequence yi tangent to the di's, the expected value of the product of the di's is less than or equal than the expected value of the product of the yi's to the 1/2. So this is helping me decouple a product of dependent variables to a product of independent variables, of conditional independent variables. And this result is sharp. So that's a best possible result. Now, okay, so let me show you an example, because then it will become more clear why this is useful. So you have, if you want to estimate the expected, the moment generating function of the d's, of the sum of the d's, the inequality that I just showed you can be used to just, it applies to that, because this is a product of e's to the lambda d sub i's. And that's the sum, so that's the sum, okay, it's the product of e to the lambda di. Okay? And what I'm saying is, so you can decouple arbitrary sums with a finite moment generating function by the moment generating function of the sum of the conditional independent ones. So in the context of Wald's equation, this tells you that the moment generating function of the sum up to t, so this is an extension of Wald's equation to Laplace transforms, to moment generating functions. The Laplace transform of the sum of the x sub i's up to the stopping time is less than or equal than the square root of expected value of e to the 2 lambda. So the moment generating function, you have to pay a price. The price is 2 of the sum of the yi's, which is the x sub I tildes up to the same stopping time. So this is an extension of Walt's equation to the case of moment-generating functions. Okay. Now, if the variables have mean 0, you can remove the square root, because the square root is unpleasant. Because this will be bigger than 1 if the variables have mean 0. So, okay, so that's a decoupling inequality, and it has many applications. And I'll show you an application of that, maybe at the end of this lecture. But, Class, he proved an inequality for Banach space variables. So the Laplace transform of the norm of a sum of independent variables up to a stopping time. Good. Any questions? Yes.
Sorry, can you just show the previous slide? Or I guess the first.
Yeah, I jumped too fast.
Yeah.
Previous to that?
Yeah, that's right.
This one?
Yeah.
Okay, yes. So, do you have a question?
No, I was just trying to, I didn't get a good look at this. I was trying to see how.
Yeah, I was accused of going too fast. And Siva was right. I have to slow down. So many years ago, I used to spend my time traveling, explaining these things. But I didn't do these things in one shot. It would take a week because it takes time to get assimilated to this. So I should go slower. But we only have 1 week left. So, and I am covering both decoupling and self-normalization. So you have to tell me when something is not clear. Questions? Yes.
Here, is n a stopping time, or it's in this inequality?
N could be a stopping time.
Could be a stopping time.
Yes. Because of the way things work, you have tangency of d sub I indicator t bigger than or equal than I to y sub I indicator t bigger than or equal than I. And so this inequality applies to the case of stopping times. So this is a Waltz inequality for products.
So this applies for stopping time because of what you explained there, right? By
Yes.
using this x tilde indicator t greater than I is a tangent sequence.
Yes.
Because of that, you can use that to
Yes,
replace n with the
and that is for arbitrary, if you have an arbitrary sequence of variables and you want to stop it at a certain point, the average of the square root, the expected square root, is going to be bounded by the expected value of the product of the decoupled ones to the 1/2.
I see.
So, yeah, so it's a fairly general inequality. And whenever you try to prove something, if you cannot do it, you go to a higher level of difficulty. Because when you prove something, if you are going to prove something for a more general, that is more general, the proof has to be easy. Because it will encompass many other possibilities. So that's what I did here. And let me show you the proof. The proof is actually very simple, as everything I do. Okay, that's not completely right because my chair would be upset if I said everything I did was simple. but at least the thing I'm showing you right now is simple. So if you have a sequence of arbitrary variables, then it is a true fact that this is a martingale. The product of the DIs over the expected value, the product of the conditional expectations is equal to 1. So then I look at the bottom. Since the expected value of DI given f sub I minus 1 by construction is equal to the expected value of yi given f sub I minus 1, and the expected yi is given fi minus 1 is the same as the expected of yi given g, which is the sigma field generated by the d's. These are bundled, but anyways, so since they are the same, I can replace these by the expected value of yi given g. Is that clear? Now, so I do that. So I start with my product to the 1/2, and I am going to okay, I'm going to multiply and divide by the product of the expected di given f sub I minus 1 to the 1/2. Okay? Then, okay, so I am putting this here, so it looks like what we showed was 1 when you square. So, and then I asked as a prerequisite for this course Holder's inequality. So we are going to use that prerequisite. So then this is less than or equal than the expected value of the product of the I over the product of the conditional expectations times the expected value of this. Okay? Holder's inequality. From here to here is Holder's inequality. You square this to the 1/2, you square this to the 1/2. Okay, so by Holder's inequality. Now, we showed that this is equal to 1, right? So therefore, the expected value of the product of the i's to the 1/2 is less than or equal than the expected value of the product of the di's, but that happens to be the same as the expected value of the product of the of the conditional expectation of yi given g, because these two are the same by construction. And then given g, the yi's are independent. So I can rewrite this as the expected value of the product because they are independent. And then you have the expectation of the product of yi's given g. And by the Tower property of conditional expectations, this is the expected value of the product to the 1/2. Okay? That's the decoupling inequality. Any questions? Okay. So now, I gave you the proof. The proof is 3 lines. You couldn't get tenure with this. So I didn't tell the chairman I was doing easy things. Or, the chairperson. Okay. Now, so the special case of that is the inequality for the moment generating function. Okay? Now, in a subsequent paper, I extended that inequality to the case where you have constraints. This is prompted by a question by Talagrand. So I showed him this inequality, and this is when he was working in his concentration of measure inequalities. His very widely acclaimed problem. He said, I showed him this, and he said, can you prove it if there's a constraint on the d's? And so I went back to work. The question is the most important thing. So he asked me a very important question. So my answer to that was this. I take a random variable which is non-negative, adapted to the d's, no matter what variable it is. Okay? Then the expected value of g times the product times the moment generating function of the d's is bounded by the expected value of the square root of the expected value of g squared times the moment generating function of the decoupled ones. So what you do is the constraint on the d's can be transferred to a constraint on the case of the y's. So you're tying things up. Okay, and this is the inequality that I used. So Doob gave me a good question. He asked me, can you extend, or he said, extend the results on harmonic analysis. And then in order to do it, I needed the help of Talleyrand. Because in order to do that, I needed to include this particular trick. And this is also a sharp inequality. And the proof is very simple again. All you need to do is multiply by g, and then when you use Hölder's inequality, it goes to the square. Okay, the same proof, but it was very successful in doing self-normalization. Now this one is stuck. Okay, good. Press escape. Okay, good. Oh no. Okay, so I will show you how to use this to do self-normalization in the second part of this lecture. We are going to take a break. So let's take a break, and I'm happy to answer any questions during the break. And after that, we're going to show how to use this to extend Bernstein's inequality for sums of independent variables to the case of Bernstein's inequality for self-normalized martingales. Okay? Our lectures asking questions. So, are there any questions? You know, because the most important thing is the question. So, you know, that's what drives research. So, anyway, so let me talk
about. Question.
Yes.
Bob and I were just talking. So, should capital T be a stopping time, or it can be any random time?
Should be a stopping time, but I have other work where you can have any random variable.
I see.
Actually, let me think. The stopping time. Okay, there's work by Yor, you know, the late Yor, Mark Yor, where he has results up to any time. But I don't remember the reference. Now I have results for first crossing time, where the process can be anything. And I'm going to talk about that in a later lecture. So you stop your process at any point, and there's a decoupling inequality, which gives you a bound on the expected time. You know, that is sharp and universal. So, okay, so now, so I'm going to talk about U statistics. And this project began by a question of Évariste-Giner. So, you know, there are a very hot topic 10 years ago was empirical processes. Okay? And so he was working on what is known as U processes, which are empirical processes of bivariate functions. I will show you examples of that. Anyway, so he wanted to extend the theory of U statistics to U processes, so which means extending it to U statistics with kernels in a Banach space. So this work talks about random variables that have values in a Banach space. But Banach space is not necessary. But that was the motivation behind what I'm going to talk about. And if you're interested in learning about that, you know, my book with Évariste-Giner has a very extensive, you know, extensive reference. It's a very extensive reference. I'll show you the book, maybe. I'll show you a picture of the book. That's on the first lecture. But I didn't present it. I was going so fast. Okay. Anyway, so it's De la Peña and Giner, 1999. Decoupling. That's the title. Okay, so what is a U-statistic? A U-statistic. So let's take a sample of independent variables. They don't really have to be IID, but independent. And for simplicity, we are going to work with IID observations from an unknown distribution. So we want to estimate the expected value of the function of a function of h1 up to xn. So now, we are interested in functions in a Banach space, for example, but the results are not necessarily tied to real valued. Now, there's a very, very widely used expansion of U-statistics by Hofting, which is like a classical result. If you want to work with U-statistics, if you want to prove limit theorems, you use Hofting's decomposition. This is different. Hofting decomposition, as far as I know, doesn't work in Banach spaces. This works in Banach spaces. So okay, so here's the definition of here's the use of the U-statistics. So we're trying to estimate the parameter theta, which is the expected value of h of x1 up to xm. And we want to get an optimal estimator now, so which is unbiased. And the way to get an unbiased estimator is to, okay, so let's assume that this variable, this h has the property that it is permutation invariant. So, it's like f of xi equal to f of xi xj is equal to f of xj xi, permutation invariant. So a U-statistic will be the best U-statistic, the best unbiased. So we call it U-statistic because it's an unbiased estimator. The unbiased estimator obtained by taking the sum of all the x's over all permutations of the x's divided by the number of entries, and that's a U-statistic. Any questions? So you see, if I want to get the expected value of U by linearity of expectation, that's equal to the sum of the expected values of the h's. So you see, if you take you want an unbiased estimator of this, the estimator, the natural estimator, unbiased, is going to be this one. You are using all the information that you have, all the x's, and you're averaging over all of them. A special case, the easiest U-statistic is the sample average. So these results extend the results on sample averages, for example, to the sample variance. So you can get estimates for the sample variance. Because the sample variance, there's an unbiased estimator, which is a U-statistic. Do you want me to show which one it is on the board? Okay, good. So what we have is x sub I IID. And let's define the sample variance as the sum of xi minus x bar. This is the average. So it's the sample average. Okay? So the sum of the squares divided by what? The sample variance, what do you divide by? N?
It depends
It depends on what?
on what you're interested in.
How you're feeling?
N minus 1.
Yes, well, you know, I teach statistics for poets. And in
Poets.
statistics for poets, you use N. Believe it or not. Yes. So if you're a poet, you use
Oh,
N.
not a poet.
Then you should use N minus 1. You see, when the students see N minus 1, they get mystified because when N is equal to 1, this is 0. So in order to explain to them, you remove the 1. Okay? So this is the sample variance. And this is an unbiased estimator of the population variance. Sigma square. So the expected of this is equal to sigma square. So this is an unbiased estimator of the sample of the population variance. Now, this can be written as the sum I going from I1 less than or equal than I less than j less than or equal than n. xi minus xj square times a function of n. I think it's 2 over n times n minus 1. So this is a U statistic, which is a sum of xi minus xj square. Double sum over all possible values of I and j. Okay? Now, this is permutation invariant because xi minus xj is equal to the square of xi minus xj square is equal to the square of xj minus xi squared. That's what I meant by permutation invariant. Okay, so the sample variance is a U statistic according to the definition. Okay, any questions? Now, I can rewrite this if I want to be. Okay, well, anyways, that's what that is. There's an issue whether or not you are adding over I less than j or j less than I, but the sum will be the same. So all you need to do is to adjust by a constant. Is that clear now? Okay, so that's an example. Now, it is very well known that the sample variance is a sum of dependent variables. Yes?
If the x's are IID, then you don't need permutation invariance for you to be an unbiased estimator, right?
If you don't need a permutation invariance for it to be unbiased. I guess you're right.
Because that's averaging over the permutations anyway.
Yes, you're right. So anyways, it is arguably true that this is a sum of dependent variables because you have x bar. So using typical probability results, it's not easy to handle it because they are dependent. And so by using decoupling inequalities, you can replace it by a sum of conditional independent variables. And then you can play as though if they were independent. And that's the magic of decoupling. Okay, so now let's see. Here. Okay, so here is the case of, in the case of 3. So So the U statistic is the sum of h of fi up to I phi m over all those divided by n choose m. That's the unbiased estimator. Okay, and here is, I jumped. I jumped. I'm sorry. Okay. So, any questions? Now, there's another statistic that is a U statistic, denormalized U statistic, which is known as the Gini mean difference. So you take the absolute value of xi minus xj, okay, and you take the average of those. That's what is known as the Gini difference, the Gini mean difference. Now, the Gini mean difference is very important for income inequalities, studies of income inequality. So, the World Bank publishes, so here's a real applied example. So the World Bank studies countries by their inequality. So income inequality. I think last year's Nobel Prize winner got it for income inequality in economics. The work of the person was income inequality between males and females. So she did some studies. Anyway, so this is relevant to that. So the way things work, suppose that the variables are positive in this case. So the variables are incomes. So you have n incomes, okay? And the empirical Gini mean, which is this, is going to be the sum of xi minus xj over n minus 1. So this is a U statistic. And the expected value of x1 minus x2 in absolute value, that's called the Gini average. That's a parameter. So if you want to estimate the expected value of that, you take a sample and take the differences. Okay? So this x sub I is the indicator of the ith individual, and xj is the indicator of the jth individual. So the idea is that this average will most likely, well, this is the Gini mean difference. But let me show you the Gini estimator, which is really what is used for, let me see if no, I don't have it here. It is used for income inequality. The Gini coefficient, the Gini mean difference comes from taking these, the Gini coefficient is the sum of these over the sum of these x's. That's the Gini coefficient. So what in a later lecture, if we have time, I would show you how to estimate the bias of the Gini coefficient, which was an open problem. So it's a problem on self-normalized statistics. So that's another example of self-normalized statistic. Okay, so now, so I'm going to, the results that I have are for generalized U statistics, and they apply to random graphs, the study of random graphs. So now I extend it. Instead of looking at 1f, I can look at functions of I and j. Okay. Okay. Another, if you use this, you can then work on quadratic forms. Okay. you can work on quadratic forms. Now, so who is interested in matrix completion? Nobody? Well, that was a hot topic 15 years ago. And the first paper on matrix completion uses our decoupling inequality to get their results running. They needed a bound on the moments of the quadratic form, and the bound was a decoupling bound. And I'll show you the inequality. Okay, so anyways, that's an application. Application is matrix completion. That's a paper of Candence and Recht, and in their paper they use the decoupling inequality. Now, so here's an example of random graphs. So you can use this to study random graphs. So consider a complete graph. So we have x sub I IID variables. Okay. Consider the complete graph G equal to VE, where the vertices, the number of vertices is n, and x sub I is the color of the vertice. If we let f sub I j equal to f for some fixed f, and if f is symmetric, then you have this. I mean, then this is a U statistic, not averaged. Okay? So you can study the U statistic using decoupling. And I'll explain, I'll give you a practical example in the next slide. So for example, suppose that you have this random graph where x sub i's are Bernoulli of P, where P is the parameter. So the vertex x sub I is equal to 1 or 0, indicates that the vertex is black or white. And f of x1, x2 is equal to 1 minus x1 times x2. Now this one is not symmetric, but still the decoupling inequalities apply. So the decoupling inequalities that I will show you apply even if the kernel is not symmetric. So then what we have is, let's look at, suppose that we want to count the patterns beginning with a white vertex ending in a black vertex. Okay, so if they begin a black, so they begin on a white vertex and end on a black vertex. I want to count how many of these there are. How many are there? There are 4, right? Okay. Now, this is a sum of dependent variables. So it's hard to handle by using the typical results for sums of independent variables because they are dependent. So it's useful to decouple it so that you can study the problem as though if the variables were independent. Now, another example of a random graph that you can study is the following one. So suppose that you have the statistic f of x1, x2, and you're trying to count the number of the patterns beginning in white vertex and ending in black vertex. Oh, that's okay. So with this kernel, you're counting the number of patterns with white vertex beginning and ending on a black vertex. Now, if you take f of x1, x2, which is an indicator of x1 different than x2, then the statistic is going to count the edges where one is black and the other one is white. Okay? And how many edges satisfy that condition? So one of them is white, the other one is black. So this is one of these edge. So that's 1, 2, 3, and then 4. Any questions? So that this statistic is counting the number of those edges. So these are useful statistics in random graph theory. Okay, so now let me show you. So what I do is I decouple these things. There's a lot of dependence there, but I decouple them, and then you can use limit theorems for sums of independent variables to study random graphs. Okay, so now I'm going to show you the decoupling inequalities. Now, so even though the sequences x1 up to xn is a sequence of independent variables, the functions, the sequence of fij, xi, xj is a sequence of dependent variables if I or j is fixed, right? Because you have f of x1, x2 is dependent with f of x1, x3. So these are dependent. So suppose that you want to estimate the expected value of a function of the norm of the sum. So these functions have values in a Banach space. Then if you are looking at a convex increasing function phi, then I can give you an inequality. Okay. Let's assume that the maximum over I different than j of the expected value of fij, xi, xj is finite. We want to bound this. Actually, I'm going to bound this for I less than j. Okay? So what we do is the same trick as before. You take an independent, as in the stopping times problem, we take an independent copy, which we call x sub I tilde. They don't have to be AID, they just have to be independent. So we have the independent copy. Then you can rewrite this sum, okay, in this way. Is the sum I going from 1 up to j minus 1, j going from 2 up to n of f of xi, xj, fij. Then the decoupled version of this is going to be the sum of fij, xi, xj tilde. You replace xj here by xj tilde. So this is what I used to call d sub I, d sub j, okay? And this is e sub j, y sub j, I'm sorry, y sub j, okay? So anyways, these two sums, the inner sum gives you the regular variables which are dependent as j changes, and this is a sequence of conditional independent variables. Once I replace xj by xj tilde. And to see that, I can rewrite this, well, if I let this to be called as tj, it's a function of the xj tildes, if you condition on the x's. Yes? So we have a sum of conditional independent variables. Okay? Any questions? So this is a sum of conditional independent variables given the x's. And pictorially, what we have, suppose that you want to study the distance between vertices. okay? The distance between vertices, the sum of all total distances. Well, you can decouple it. You throw, so you have a sequence of points, x1 up to xn, x1 up to x4. You throw another sequence, x1 tilde. Actually, in this case, since I'm just having I less than j, then I only need to use j bigger than 1. Okay? So the decoupled sequence for this will be you take x2 tilde, x3 tilde, and x4 tilde. So the distance of these ones can be studied by the distance of these ones, by these distances. Now, so I go back and now I'm taking I different than j. So I throw a curveball on you. I throw a curveball on you. So, but the results are true whether I less than j or I is different than j. And this is the result. The expected phi of this sum is less than or equal than the expected phi of A sum of f sub ij of xi xj tilde. Oops, danger everywhere. Sorry. Okay, so if the FIFJ satisfy the symmetry condition, then you can get a lower bound. So for arbitrary functions, you have the upper bound. And if you have symmetry, then you have a lower bound. The constant for upper is 8, the constant for lower is 4. Now, this is something that probably is not important, you know, so let's skip it. I mean, at least this part. But this is important. You know, Vershnin, who knows the book by Vershnin? Okay, so he writes on infinite dimensional statistics. He has a very famous book. In his book, he's using an inequality of this type. He proves it. So what you have is x is a sequence of mean zero variables, IID mean zero variables, and he gets that the expected value of the sum of AI xi xj is bounded by the expected value of the sum of AI j xi xj tilde. Okay? Now, so he's using that inequality. Now, I have to tell you, there's a Fields medalist. His name is Jean Bourgain. Okay? And he came up with the upper bound. I don't think he had the lower bound for non-negative variables. So Vershnin shows how to obtain the upper and the maybe he only did the upper bound. Okay? I have to go back. But I have both the upper and the lower bounds with the same constant, 4. And this is useful in the theory of random matrices. Because you have a matrix A, where A is equal to A transform AT, then this inequality holds. Okay, so if you specialize to the case of quadratic forms, then you get this. I'll show you the proof. Okay, so let's go to the next thing. Okay, yeah, for these inequalities holds for any convex functions and any mean zero variables. But what we do is we don't assume mean zero. Okay, so now it's a warm-up lemma, but maybe it's a cool-down lemma. So yeah, this is a little confusing. So let's take a couple of minutes break, and then I go through this and show you the proof with a 4. Okay? I think that's all we will be able to do. But let's take a couple of minutes so I show you that. Now I'm realizing I'm going really fast. So you should stop me. You should ask me questions. Okay, so of the inequality when you have mean zero variables. So the first lemma is a very easy lemma. You know, the law of large numbers, the proof of the law of large numbers for sums of IID variables relies on this lemma. And I can show you the proof, but it is by using a martingale approach to proving the law of large numbers. So this lemma is important. So if we have IID variables x1, x2, and we define z to be c1 to be c1 is x1, x2 with probability 1/2, and c1 is equal to x2, x1 with probability 1/2. Then this expectation is equal to x1 plus x2 over 2. Now this is a little more confusing than what is easy to prove. So let me show you the actual lemma that we use to prove the law of large numbers. So here we have x sub I IID, and we are looking at the expected value of the sum of x sub I. Okay, no, I'm sorry. So I want to estimate. Did I go to another page? Yeah. So I want to find what this is. So these are IID. I want to find. There we are just looking at the case of 2, but the general result is this. This is equal to the sum I going from 1 up to n x sub I over n. Okay? Can someone prove this? Come to the board and show the proof. It's a one-line proof. Everything is easy. I guess, yes, how do you do it?
Sum of xi from 1 to n. Like look at the expected value of xi given xi x1 plus up to xn. Sum of all of that should be equal to sum of xi's.
Yes, good. So you have very sharp individuals here. So what we have is that the sum, since this is equal to that the sum how to prove this, you have the expectation of the sum. If I add these expectations, the sum of the expectation of xi given x1 up to xn, given the sum of x1 up to xn, this is actually equal by linearity of conditional expectation. This is equal to the expectation of the sum of x sub I But what is this? I have this random variable is the same as itself. So this is equal to the sum of the x sub i's. And this is actually equal to n times the expected value of x1 given x1 plus up to xn. That's the proof. And that's, I did it the way he suggested, right? Okay. So, because you can take then n to the other side. So that's the proof of that fact. Now, this is a reverse martingale. So if you know martingale theory, there's a reverse martingale law of large numbers. So if you have a reverse martingale, it will converge under certain conditions. And so that's the proof of the law of large numbers for IID variables using martingales. Any questions? So this lemma is very basic. Now, this is just a complicated version of it, but it is needed to extend this lemma to the case of functions of two variables. So let's show how to extend it. So suppose that you have the f sub i's, the sigma field of the c sub i's, where c sub I is a sequence of independent random vectors. C sub I is equal to xi xj tilde, I guess, with probability a half. Let me see. C sub I is x sub I xi tilde with probability a half, and C sub I is equal to xi xj tilde with probability a half. Then the expected value of f sub ij of xi xj given the sigma field generated by this is going to be the same if you replace xj by xj tilde because of the sigma field that we're using, and the same for all of them. Okay? Then you use the trick that I use here to prove that this is equal to 1/4 of the sum of the fi xj. Okay, so this was the most difficult part of the proof, to extend the case of IID to the case of bivariate functions. Okay, so I'll show you the full proof based on this in 5 minutes. So we have this identity. Suppose that I let x script to be the sigma field generated by the x's. Then this sum is going to be equal to, you can, by using addition and subtraction, what is this expectation? Expected of x given fij of xi xj. What is it? If you don't know that, then we cannot continue. Yes?
It's just itself.
It's itself. So I have this summation, which is equal to this. Then I add 3 terms, and then I subtract them. So they are exactly the same. Okay. Now, by the lemma that we just proved, this expectation is equal to this. Okay? If we assume, okay, here, if we assume that the expectations are 0, like, okay, so if you assume that the expectations are 0, you see, we could also have it for fij. So, any function. But Verschnin, he does it for quadratic forms only. So, but anyways, if you have this condition, which in quadratic form it means that the x sub i's have mean 0. Okay? then I will give you the proof of the decoupling inequality. So then we have that this expectation, because of the lemma, is equal to the expectation. So suppose you have a convex function. Then the expectation of this is equal to this, the expectation, conditional expectation of these ones. Why? What is the expectation? Excuse me?
0?
It's 0. So then by conditional Jensen's inequality, since this is fixed, when you fix x, this is going to be the expected value, and then you can use Jensen's inequality. Conditional Jensen's. But we know that this by the lemma is going to be, I replace this thing by 4 times f sub ij of f of xi xj, and I have this equality, and then I can use Jensen's inequality, conditional Jensen's, to get this. So the proof is actually 1, 2, 3, 4 lines. So as you see, all the proofs are easy. And I succeeded. So I have shown you the upper bound. For the lower bound, okay. No. What about if, so just to finish, what happens if the functions don't satisfy this assumption? If the functions are not necessarily mean zero, then the things get complicated. And in that case, it becomes more complicated, and we have to multiply by 8. This would be 8. And that's the biggest difficulty that I had to confront was the fact that to change this from the case of mean zero to the case of arbitrary functions. Yes?
Confused about the third line. Didn't we assume the expectation given the script x, f of xi, xj tilde is 0?
That's z, that's not x on the third line.
Oh, the z. Okay.
Yeah.
So you're using, the phi is a convex function.
Yeah.
Okay, and this is the one where you have the knowledge of f of xi xj up to x. Okay, here you don't know whether or not xi is the same as xj or not. Which one it is? Okay. Anyways, so maybe I will give you the general proof. But that one is more complicated, and you can vote. If you want to see this, I can do it next session. It's more than 4 lines, but it was a very key result in decoupling, because it allows you to treat situations where the variables don't have mean zero. Okay, and there's a little trick that I use to do that. So next time we begin proving that one. Okay? Any questions? Any questions? Okay. So I'm not going to prove this, but the inequality is also true for tail probabilities. So there's a CK for which this is the upper bound holds, and if the functions are symmetric, then the lower bound holds for every t. Now this result was originally published in the Bulletin of the American Mathematical Society, and at the time the bulletin only published what it considered, by invitation, what it considered the top 10 results in all of mathematics for the year. So it's not a trivial thing. The proof of this is not something I can show in one lecture. Okay, thank you. It's a result with Stephen Montgomery Smith, who is a functional analyst. Thank you.